How does vector calculus explain electric and magnetic fields? Imagine a world where invisible forces shape everything around us. These forces are electric and magnetic fields, and vector calculus is the key to understanding how they work. Electric and magnetic fields are like invisible lines that fill space, each with a strength and direction at every point. Think of them as weather maps showing wind flow, but instead of air, they show forces acting on charges and currents. These fields change over time and space, which makes their study complex but fascinating. Vector calculus gives us the tools to describe these changes precisely. The first tool is the gradient, which tells us how a scalar quantity like electric potential varies in space. For example, the electric field can be found by taking the negative gradient of the electric potential. This means the electric field points in the direction where the potential drops fastest, guiding charges along the path of least resistance. Next is divergence, which measures how much a field spreads out or converges at a point. For electric fields, divergence relates directly to the presence of electric charges. If there is a positive charge nearby, the divergence of the electric field is positive, indicating a source. For magnetic fields, divergence is always zero because magnetic monopoles do not exist, meaning magnetic field lines never start or end but from continuous loops. The curl is another important operation. It measures how much a field rotates or circulates around a point. In electromagnetism, the curl of the electric field is linked to how changing magnetic fields induce electric fields. This is described by Faraday's law, which states that a changing magnetic field creates a curl in the electric field. Similarly, the curl of the magnetic field relates to electric currents and changing electric fields, as explained by the Ampere-Maxwell law. All these operations come together in Maxwell's equations, which are the foundation of classical electromagnetism. These equations use vector calculus to describe how electric and magnetic fields are generated by charges and currents, and how they influence each other over time. For instance, Gauss's law for electricity shows that electric fields originate from charges, while Gauss's law for magnetism confirms that magnetic fields have no beginning or end. Faraday's law explains how a changing magnetic field induces an electric field, and the Ampere-Maxwell law describes how electric currents and changing electric fields produce magnetic fields. In electrical engineering, understanding these concepts helps us design everything from transformers to wireless communication systems. When engineers analyze how a current in a wire creates a magnetic field, they use the curl operation. When predicting how electromagnetic waves travel through space, they rely on these mathematical tools to solve complex field equations. Potentials also play a role in simplifying these problems. The electric scalar potential and magnetic vector potential allow engineers to break down complicated fields into easier-to-handle parts. The electric field can be derived from the potential by taking its negative gradient, and the magnetic field can be found by taking the curl of the magnetic vector potential. In the end, vector calculus acts as a bridge, translating the invisible forces of electric and magnetic fields into precise mathematical language. It helps engineers predict how fields behave around wires, capacitors, antennas, and other devices. Without it, designing and understanding modern electrical systems would be nearly impossible. So, in essence, vector calculus is the language that explains how these fields exist, change, and interact in our electrical world.